next video. Ladies and gentlemen, this one is about geometric mean. Alrighty, we just did the proof on the last page. We're going to do some geometric mean problems here. Recall the geometric mean is given by the square root of a times b. This is the only thing not given to you on the formula sheet. You've already seen where we get this derivation. It's by using similar triangles, which I'll show as I work these problems down here. For these first ones up here, you just need to know how the geometric mean is calculated. Again, not given on the star chart. This is something you actually have to memorize, something you'll actually need to know. All right? In any case, to find the geometric mean, all we'll do is we just say the geometric mean is given by the square root of the first number times the second number, 4/5 times 2. Alrighty. So to simplify this, I'm just going to multiply fractions. 2 times 4/5 is just 8/5. Alrighty. And you can simplify this further if you so choose. This is honestly a perfectly valid final form. What you could do to go further here is maybe take the square root of 8 over the square root of 5. Remember that radicals love multiplication and will dissolve over them. Division is a form of multiplication, so that's okay. And then here, square root of 8 divided by the square root of 5. We could remove the 4 from this guy and rationalize the denominator. So up top, we have a 2, root 2, and then I'm going to leave the root 5 on the bottom for now, and then I'll choose to rationalize the denominator. All right, and on the bottom, we'll have root 5 times root 5, which is 5, and 2 stays, root 2 times root 5, which is root 10. Look at that. Okay, honestly, what am I trying to say? We're opinionated as mathematicians of which one of these forms is simpler. Whichever one you end up finding in the problem is fine for you. Alrighty. And let's try the next one as well. Here we have the geometric mean of 12 and 5. 12 times 5 is 60. I just wrote the same thing twice. 12 times 5 is 60. We're looking for, remember that the square root loves pairs. The name of the game is pairs of numbers. So in here, are there any products of pairs you may spy? I detect a pair of 2s. I guess that's all, right? I'm just going to say this is the same as the square root of 4 times 15, right? 4 times 15 makes 60. And then here, think of like, a quarter hour. And then here, we'll take 2 times the square root of 15, and we're done. Very nice. 4 is a pair of 2s, so the 2 comes out of the radical. Very nice. Down here, we'll try the geometric mean in action. I'm going to show, I believe in class I showed you guys the similarity method on this one. So I'm actually going to do the memory. I'm going to do the memory method here. So if you're a memorizer, I'm going to go through and label my triangle is the first thing I'll do. I'm going to use a red color to not confuse it with my work, which I'll do later. This is the letter A. This is the letter B. Inside, we have the letter X across the entire triangle. Down here, we said it's the letter C. And inside, we have the letters D and E. Okay, so in red, this is the label that a memory person would be memorizing. This is their layout. The sides of the triangle are always A, B, and C. The parts are D and E, and inside, the altitude is always X. So here, the memory person would then recite. There are 2 possible formulas which can be useful to me. X squared is equal to D times E. The red X, I'll say. Now, X and X, they happen to coincide, but notice like A, D, and E, right, are actual numbers in this case, but in a second, I'll show what I mean in a second. And then here we have A squared is equal to, and it would be D times C, or C times D. So notice, D here and C, A is actually the letter Z, right, whenever I solve the problem, but this is what the formulas access in memory. So, in any case, we can quickly solve for a couple of these sides. We see that X is equal to the square root of, I should say, maybe to stay precise with the formula, I'll say that X squared is equal to D times E, which is 5 times 15. Alrighty. To calculate 5 times 15, we know that 3 times 15, or that we know that 4 times 15 is 60. We just saw that. So this answer is 75, and X is the square root of 75. I don't know why I wrote that so poorly, which simplifies to 5 root 3. There's a pair of 5s in there, right? 25 times 3. Pair of 5s in there. So X, this is our answer for X. Now, if you were on the test, I would make this as clear as possible to me, your grader, whose job it is to give you a good grade, right? Make it as easy on me as possible to detect the work you have done and which answer you are answering, I guess, like which actual variable you're answering. In any case, we'll continue forward. We can also use our other formula here to get z. We see that z has got to be equal to 5 times 20, since c is the whole length is 20. So we'll write that out. A squared is equal to CD. In this case, A is played by Z. Alrighty, and then D and C would be 5 times 20. 5 times 20 is 100, and the square root of 100 is 10. So Z is 10. This one happened to work out. It's uncommon that on the geometric mean, you will have whole numbers. It's typical that you have an irrational number. That's totally fine. This is a rare case that you end up with a rational number. In any case, we'll finish off here by getting y the same way. The memory person appeals to their same formula. Notice that this triangle can be flipped and the properties behave the same way. Therefore, y and 15, since they're the closer sides, and then we also have the 20 for the total of c. So we know, again, a squared is equal to c times d. This would be like, this is the memory person doing an inside, then doing an outside, then doing an outside again. And here, this time, y is being played, or a is being played by y, which is equal to 15 times the total, which is 20. All right? And so y is the square root of those. And let's see, 15 times 20, we have 300 there. And also, obviously, this is 100 times 3, so 100 is perfect square, so 10 comes out of the radical, 3 remains. Very nice. Look how clear and simple and concise the memory method can be. It's very elegant. Like, you just write the answer down and it works. All right? This is because you're not doing a lot of the work. Your memory is doing a lot of the work. You are not really doing math here. You're just reciting a process. You're not thinking. You're just doing the thing that I told you to do, which is great. I mean, it works. Don't get me wrong. It's beautiful. It works every time. You'll never fail as long as your memory serves you correctly. All righty? This is my personal favorite method. This is the Shizzle approved method over here, the similar triangles method. Alrighty? I'm not going to hark on you if you choose to memorize things. I know that one day you will grow up and not have to recite similar triangle methods to your math teachers anymore. So it's fine if you want to memorize and forget later, but similar triangles will teach you to quantitatively reason now and forever. Anyways, what I'll say here, similar triangles are very elegant. To do this, we just split the triangle up into its 3 obvious pieces. Here we have the large triangle, which is triangle GHK, in case you're curious. It has a long leg of Z, a short leg of Y, and a hypotenuse of 9 plus 3 for a total of 12. All right? On the next side, we have a medium triangle. So I'm going to draw the next biggest one. Notice that the medium triangle's long leg is here. It's given as 9. The hypotenuse is Z, and over in the altitude here, which is the short leg of the triangle, is given as X. And then for our tiniest triangle of the Russian nesting doll triplet, we have 3 as our short leg, Y as the hypotenuse, and finally X as the long leg. So the cool thing about the similar triangles method is as long as you draw this picture correctly, you can do whatever you want. You can do Pythagorean theorem, you can do geometric mean, you could do similar triangles, right? This is just classic right triangle nonsense, and mathematics is math, and what am I saying? Math is math, and it always helps. To find my first one, to find my first proportion here, I'm searching for something that has one repeating variable to make it as easy as possible. The first thing I just happen to glance at that I see is Z going with 12. This is long leg hypotenuse. Long leg hypotenuse. We also get Z and 9. Okay? This is a good proportion because it only has one variable. An example of a bad proportion would be, say, mixing Z with Y and 9 with X. That proportion would have 3 variables, which is almost impossible to, borderline impossible. I mean, if you didn't know, possible. Barely possible to solve. This one is much, much easier, and I'll show you why. Okay? Here, we'll write the fraction Z out of 12. So this is me solving for Z. Z out of 12, and then is equal to 9 out of Z. So notice, look, I went from long leg to hypotenuse, so I did the same thing on this triangle. Long leg to hypotenuse. Very nice. And so, we'll cross multiply here to get that z squared. It's got to be 9 times 21, which is exactly what the memory person would have achieved. If they had done, the memory person would achieve exactly this if they had done something similar. Why did I put 21, though? I meant to put 12. It's an odd choice by me. Whoa. Oh, my God. And on camera. I'm just going to restart. That's crazy. I did it twice. I almost did it again. I genuinely almost did it again. Oh, my gosh. There's not enough coffee in the world. Anyways, so z squared, and then I'm going to square root both sides here. All right. I see that there's going to be if I take this 4, if we square root 9 times 12, right? Here, what I see is a pair of 3s and a pair of 2s. So those get to come out of the radical. 3 times 2 is 6, which leaves us with 6 root 3. Okay? Calculator trick still works if you would rather do that way. And now, fortunately, that I have done the geometric mean to find one of the answers, I can actually solve the rest of this problem using Pythagorean theorem. So now that I know that z has to be 6 root 3, I'm just going to plug that in over here. And now, look, I see lots of triangle relationships where I could use Pythagorean theorem. Like, look, I know these two sides of the medium triangle, so now I can find x. We'll say that by Pythagorean theorem, x squared plus 9 squared is equal to 6 root 3 all squared. I'm using the medium triangle, so z is the hypotenuse, 9 is one of the legs, x is the only missing leg. Now, we'll subtract 9 squared from both sides after squaring this, and notice 6 root 3 is really the square root of 9 times 12, right? So when I square this, I should get back to 9 times 12, right? So I don't have to do any extra work there if I'm clever enough. I don't know why I did that. I was going to subtract that, but that's fine. And we have, sorry, I think I just made a crazy mistake. No, just kidding. No, I think we're fine. I believe this is 96. 108, sorry guys. 108, beautiful. 9 times 12, of course it's 108. And then here we'll have x squared equals, and we'll subtract 81 from both sides. I don't know why this is becoming so hard for me today. I'm tired, I guess. My mental math is failing me. Let's see here. That's what the old calculator's for anyways, right? 27. How lovely. Okay, so here we get 27. And of course, x must be the root of 27. This has a factor of 9 times 3, so this is a simpler form would be 3 root 3 for the value of x. Now that I know x, I can go back and plug it in, and then use Pythagorean theorem again to calculate the value of y. Alrighty? So, I'm going to do that same thing. I'm going right here now. 3 squared plus x squared equals y squared. Look, it's literally like dominoes. I found z, then I can find this one, then I can find this one. Right? So, for example, here I have x squared, which we know, so I didn't mean to write that. Let's see. I have 3 root 3 squared plus, and then here I'm solving for y squared, so it's the unknown. And 3 root 3 squared, we already said earlier, well, no, we have not said that, I'm sorry, is actually going to be 27, right? So we'll take 27. Look, you can literally see, like, this is x squared. X squared is 27. It says so right there. So I'm going to put 27 here. There's no extra work, right? If you're paying attention to what's going on, you can avoid doing a lot of work, right? Plus 9 equals 2. If you're intentional, I want to say. If you're intentional about what you do, you can avoid a lot of work. And here we get y is the square root of 27 plus 9, which is the square root of 36, which is, of course, 6. Very nice. So y did happen to be rational in this case. And look, it's very obvious what I did. Look, do you see the way I wrote my work? It's very obvious what I did. I said similar triangles. Then I made a proportion where I drew a picture using similar triangles to find z. Then, like dominoes, they unraveled using the Pythagorean theorem. Very nice. There's much more room on the test, I will say. There's much more room to sprawl out, but also scratch paper is allowed. So it's not like, you don't have to be able to fit your work this compactly. Anyways. Guys, as you continue through these, you'll see that all these questions are exactly the same. Okay? Okay, there's only one way to do a geometric mean problem, and we are totally done with that part. So I've shown these are the two basic ways to achieve similar triangle success. Do I want to show another way? No, I think that would be too much at once. Both of these ways are great. I encourage you guys to try the memory on this one, try the similar triangles on this one, however you want to do it. You don't have to be able to do it both ways. Pick your favorite method, whichever one is easier for you. If you like the quick and dirty memory method, then you go right ahead. If you like the deep, thoughtful, similar triangle method, this is the one of intellectuals right here, baby. You will see your results all the same. Alrighty? I'll see you in the next video.